Hello, welcome to the SETI Colloquium series. It's our great honor today to have Marie Madigan giving us a talk about the bizarre orbits of outer solar system minor planets. Anne-Marie went to her undergrad in Galway in Ireland, and then she got her PhD from Leiden in Netherlands. And she has been at Berkeley as Einstein and TAC postdoc for the last couple of years. And probably all of you have heard about Planet 9, and that planet might or might not be there, but what is certainly there is a very strange pattern of orbits of trans-Neptunian objects. And today, Anne-Marie will tell us all about that.
Okay. Thanks so much. So can you hear me okay? The mic works? Great. Okay, so thank you. Yeah, today I'm going to be discussing the bizarre orbits of minor planets in the outer solar system. And the takeaway message from this talk is that our outer solar system needs more mass to explain these orbits. So that mass could be in a single planet, for example, the planet 9 that came, the evidence for which came out last week. Or what I'll argue today is that it could be that there are just many more minor planets than we thought in the outer solar system that actually cause their unusual clustering themselves. Okay, so these minor planets, they're very small. And first I want to say I'm going to be using the term minor planets and dwarf planets interchangeably in this talk. What I mean by a minor planet or a dwarf planet is something between the size of an asteroid, which is this irregular rocky body, but something smaller than a planet. So a minor planet has enough gravity to make itself round, but a planet will have even more gravity such that it will scatter everything out of its way, whereas minor planets don't do that, so they tend to come clustered together in regions of space. Okay, so I'm showing our largest known dwarf planet, or minor planet, Neptune, here. It's an image taken by the New Horizons spacecraft. Pluto, thank you. Wow, yeah. Thank you for telling me. Yeah, that's not Neptune at all. Neptune is a planet. Okay. Controversial. Okay, this is our largest known dwarf planet by size, not by mass. And why I'm showing it here next to the image of the Earth is to show you just how small it is. If we plot a couple of arrows on these images, you can see that the radius of Pluto is roughly equal to the length of California. And you can drive the length of California in a day if you really had to. It would be a really long day, but you could do it. And the funny thing about Pluto is its rotation period is 6 Earth days. So you could drive the circumference of Pluto in 1 Pluto day, because 6 is roughly 2 pi. So these objects are really, really small. But where do they come from, and where do we see them in the solar system, and why do we care about their orbits? Why do I say there are bizarre orbits that need some extra explanation? So to answer that, we're going to have to go back about 4.6 billion years ago to the formation of the solar system. So we think the solar system formed when part of a giant molecular cloud collapsed. And the central part of this collapsing matter formed the star, with the remainder forming a protoplanetary disk out of which coalesced the planets. I'm going to show here the outer gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. And of course, many other planets formed, the terrestrial planets, and also minor planets, and a lot of other debris, asteroids, comets, things like this. So early on in the solar system's formation, these gas giants were moving about quite slowly because of gravitational interactions with the remaining debris. Jupiter in particular, we believe, moved inwards due to these interactions, whereas Saturn moved outwards. And at a certain point, they crossed what's called a 2-to-1 orbital resonance. And what that means is that Jupiter orbits the sun once, every time Saturn orbits the sun exactly twice.
Other way around.
Jupiter orbits once and Saturn orbits twice.
No, they're not going to switch. So Jupiter orbits twice, Saturn orbits once.
Jupiter's on the inside, Saturn. Oh my gosh. Okay, thank you. Yes, exactly that. It's a 2-to-1 resonance. Jupiter's on the inside. Okay, when this happened, the outer solar system, we believe, became quite violently destabilized. And that pushed Uranus and Neptune in particular outwards. And now when Neptune in particular got pushed outwards, it scattered a lot of this debris in the protoplanetary disk to the extent that the disk actually expanded, and the outermost regions of the disk now are known as the Kuiper Belt. We believe also that Jupiter scattered a lot of objects onto extremely highly elliptical, highly energetic orbits to form the Oort cloud. And many other objects got scattered inwards into the inner solar system. And we have evidence for this in the cratering record of geologically inactive surfaces of the inner solar system, such as the moon. So the minor planets I'm going to be talking about are mainly outside the orbit of Neptune in this Kuiper Belt, or even beyond, in between Kuiper Belt and Oort cloud. So this shows you where they are, but what do their orbits look like? And to explain their orbits, I'm going to show two of the orbital properties of these objects. It's the shape of their orbits, which are defined in two ways. The first is the semi-major axis of an orbit, which is twice or half the length of a major axis of an ellipse. So this is shown on the horizontal axis in units of AU. 1 AU is the distance from the Sun to the Earth. So the Earth is shown here at 1. On the vertical axis, I'm showing how eccentric an orbit is, going from a circle, or an eccentricity of 0, all the way up to a highly radial orbit towards an eccentricity of 1. So this tells you how big an orbit is, and also how circular or eccentric it is, how elliptical. So all the major planets, the outer gas and ice giants, are along the horizontal axis, because there are mostly circular orbits and coplanar orbits. Jupiter, Saturn, Uranus, and Neptune. And then we have Pluto, that has a significant eccentricity. And Pluto is a part of the Kuiper Belt, as I've discussed. And the Kuiper Belt drops off quite sharply after a distance about 50 AU. So it extends from Neptune's orbit to about 50 AU. Neptune's orbit is about 30 AU. Okay, extending out of the Kuiper Belt and even beyond is a distribution of small icy bodies known as the scattered disk. And as they have larger semi-major axes, or larger orbits, they get more and more eccentric. And they follow this line coming out of Neptune's orbit. So to explain what that is, I'm going to have a little interlude on gravitational scattering. So what I'm showing here is Neptune scattering a minor planet. So Neptune's on the orbit. I'm not going to point at it. Neptune's at going around the Sun in a circular orbit, and the minor planets on the elliptical orbit outside. So if we look at snapshots ahead in time, these two bodies are likely to have a gravitational encounter at a position called perihelion of the outermost ellipse. And that's the position of closest approach to the Sun that the minor planet will take along its orbit. And that distance, that equation shows, is semi-major axis times 1 minus eccentricity. So at this position, Neptune is likely to give this minor planet a gravitational kick that will put it onto a higher semi-major axis orbit. Now, this orbit will still contain the point it came from, so it will come back to this position again. And so we say the distance of perihelion is conserved. So from this equation, you see if you get a higher semi-major axis, you also have to get a higher eccentricity in the scattering process to conserve perihelion with Neptune. Okay. That's just another more highly eccentric orbit. Okay, going back. This is why the scattered disk objects tend to follow this line of constant perihelion with Neptune. As they get further out from the Sun, they get more eccentric. So it looks like we can explain these populations in the outer solar system just fine. But there are these objects that we don't understand, and these are called detached objects. And so they look quite similar to the scattered disk objects, but they have higher semi-major axes. But their eccentricities are too low to have perihelion consistent with being scattered by Neptune. Their perihelion distances are too large, and that's why we call them detached, because they never interact with any of the inner solar system bodies. So these are the objects I'm going to be focusing on in this talk. Okay, so if we look at these objects, we have the Kuiper Belt that looks like it's very ordered in semi-major axis space. Got the scattered disk that looks very ordered in this perihelion space, you could say. Detached objects look more like noise when we plot the shapes of the orbits. But they have their own structure. We just have to look at them in a very particular way. So I'm showing this here. This is by Trujillo and Shepard in 2014. This is the discovery paper that's led to all these claims of a Planet 9 evidence. What I'm plotting here is quite similar. On the horizontal axis, we have semi-major axis space. Now it's on a linear scale, whereas before it was log. So we're starting with roughly Neptune's orbit at 30 AU. I'm plotting all the way out to about 600 AU. But now on the vertical axis, I'm plotting omega, which is argument of perihelion. And I'm going to explain exactly what omega is in the next two slides. But what I want you to take away from this slide now is that up until about 150 AU, omega values are randomized, which we would expect in the solar system due to scattering events. But beyond 150 AU, these omega values start clustering. And there's only about 13 objects here, but we're bound to find more. And this is statistically significant. OK, so what is omega, and why is it interesting that these values are clustered in this variable? OK, omega has to do with not the shape of an orbit, but to do with how it's tilted in its reference plane. So we could take the plane on which the major giants are orbiting as the reference plane. To describe how an orbit is tilted, we can use two vectors. One is the angular momentum vector, which I've depicted with the letter J, and that goes normal to the orbital plane. So that tells you how your orbital plane is oriented. And there's an eccentricity vector, and that points to the position of perihelion, your position of closest approach in your orbit. So that tells you everything you need to know about how an orbit is oriented. Omega, the mathematical definition, is the angle between eccentricity vector and the vector which points to ascending node. So that's not a very intuitive explanation, and I'm not going to proceed with that. Instead, I'm going to use the analogy of a boat. And this actually, I think, works very well. So just like a boat has three ways of rotating, an orbit also has three ways it can rotate. The first is that a boat can pitch. It will either pitch forward or backward. And that's equivalent to an orbit pitching over its minor axis or its short axis, forward or back. The next thing a boat can do is roll. So you can roll from left to right in a boat. And that's equivalent to rolling left or right as you're orbiting over your major axis. And finally, the last rotation a boat can have is yaw. And that's rotating your orbit around the mast, so just redirecting where the boat is pointed. And omega, it turns out you can write as a ratio of how much you pitch to how much you roll. It doesn't matter how you yaw. OK, so this is quite interesting. An analogy I use is if you think about looking out onto the bay and you see a whole bunch of boats, and they're not co-located, and they pointed in completely different directions. But if you take a snapshot at a given time and calculate how much all those boats are just randomly pitching and rolling, you would notice not only are they all pitching in the same direction, either forward or back, and rolling in the same direction, either left or right. They're doing it by the same ratio, no matter where they are in the bay. That would be really strange. And so this is why it's so strange that these minor planets in the outer solar system are doing this. You would expect that to be completely random. What does this look like geometrically before we get into any explanations? What I've plotted here are a distribution of orbits. So we're looking outside it. This would be like looking back onto the solar system. I've given them all equal inclinations. And on these plots, they're all quite low inclinations. This is when your omega values are randomized. And on the right-hand side, you've got when omega values are all exactly the same, which is minus 20 degrees, roughly to match what we see in the data. Now, if we increase the inclination, on the left-hand side, you see that this disk kind of puffs up, like you would expect from a scattering process if you started initially with low values of inclination and gravitational interactions made things move around a little bit more. And if you can continue, you get something that looks more spherical, like the Oort cloud, for example. But now if we move on to the right-hand side, we see something very different. If you have the same omega values and you increase your inclinations, the orbits lift off the disk, and their eccentricity vectors all start pointing downwards in this example. If an omega value is different, they might point upwards. And as you go to even higher inclinations, oh, that's kind of cut off, you see that it really looks more like a cone shape than a puffy torus shape. OK, so that's what the data are looking like. And it's very strange. We haven't seen that type of structure in the solar system before. So to summarize, before I get into explanations, there are three major mysteries in the minor planets beyond the orbit of Neptune. So first of all is that we have detached objects with perihelion distances greater than 40 AU, and Neptune's semi-major axis is 30 AU. So we can't explain these orbits through scattering with Neptune. The second thing is that I haven't really gone into in much detail is that all of these objects have very high inclinations. And now you might expect that if you wait a long time through gravitational scattering, that some would reach very high inclinations. But none of them actually have low inclinations. And that's not what you get from a scattering process. You need something else to be at work to get all of the orbits off the original orbital plane. And lastly, these detached objects are all clustered in this omega value, meaning they all tilt and they all roll. And the data show they all tilt forward and they all roll to the right, just if you're interested. OK, how can we explain this? I think right now there are two scenarios that are really promising. And the first is that some external perturber is forcing them onto these types of orbits. And this is a very exciting possibility. And the paper came out last week by Madigan and Brown. And they're calling this Planet 9. And so they say they can explain all of those observations if there's an external, meaning a planet with a greater semi-major axis, about 1,000 AU, eccentric, about 0.6 eccentricity, giant planet, but more like 10 Earth masses, something in that range. And they don't describe exactly how the mechanism actually works, but they say that this planet can not just explain all those previous observations, but they will actually shepherd a lot of these planets together. So their eccentricity vectors are pointed in the same region of space. So there's only 6 orbits that look like they're clustered in space. So we'll have to see if there's more data becoming available to support this, this new idea. But it's extremely exciting. And they say that they will detect Planet 9 within the next 5 years if it's there. OK, so this is a really exciting possibility. And there'll be more papers on exactly how this mechanism actually works, how it produces all these observations. What I'm proposing today, however, is something that on the face of it is a little simpler. Although, yeah, there are some timescale issues that we need to work out. And that's that minor planets, through their own self-gravity, can actually self-organize into this structure. OK. So you might be asking the question and be quite skeptical of this idea, because we've studied the inner solar system for so long, and there are no structures that look like this. And the reason for this, I'm going to claim, is that the inner solar system has objects that are mostly on circular orbits, at least all the major giant planets. Whereas in the outer solar system, because of this scattering off the giant planets, all of these minor planets are on highly eccentric orbits. You could see that from the plot I showed you with the detached objects. And highly eccentric orbits act in a very different way than circular orbits. In particular, scattering isn't the dominant gravitational interaction process that's most important. But it's something that's called gravitational torquing. So I'm going to have another aside of this with this type of dynamical mechanism. So what I'm showing here are two minor planets on eccentric orbits around the sun. And if I can come back to the analogy with the boat and focus on yaw. So I said yaw is when you rotate the boat around the mast. And if you can imagine for eccentric orbits, that's equivalent to having a really, really, really long boat. And to yaw, to completely reorient the boat, it's going to take a lot of force if your boat is extremely long. So in the same way, eccentric orbits, they need a lot of force to reorient themselves. So if two orbits start close by, they remain close to each other over very long timescales. Now, instead of taking a snapshot of this system, I'm going to propose we take a time lapse of this system. So over many, many orbital periods, what will this system look like? So you can imagine the mass of the planet will look like it's spread out along its orbit. And there will be more mass located at aphelion than perihelion. So aphelion is the position furthest away from the sun on your orbit. And the reason for that is planets travel much more slowly at aphelion than perihelion, when they're whipping around the sun really fast. And so in the snapshot, you're going to see more mass located at the outer edges. So now, instead of having two planets that could scatter off each other, what's really important is this long-term gravitational interaction they have between each other's orbits. In fact, these orbits are going to feel very strong gravitational forces because they're persistent over many orbital periods. And I'm going to introduce a couple of equations that I'll use in a few slides at this point. If we were to pick a point along this orbit, we could calculate the angular momentum vector of that orbit, which I said is normal to the orbital plane. And you could get that from looking at the radius vector and cross it with the velocity vector at that point, and you get the angular momentum vector. These orbits are going to gravitationally torque each other. And the torque is a rate of change of angular momentum. And you can calculate that from the radius vector crossed with the gravitational force vector. So you can actually quite easily and schematically see what these orbits are going to do to each other. And if we're looking down onto the plane here, they will be changing each other's eccentricities in this scenario. But if they're tilted with respect to one another, they're actually going to change the orientations of their orbital planes. Okay. Right. So the next two slides will possibly be the most difficult in the talk, but I hope you come with me here, because the mechanism is actually surprisingly simple for how these orbits manage to torque each other in such a way that they cluster into this cone shape. So I'm going to propose that I'm setting up a simulation of a bunch of high eccentricity orbits, and they feel the gravity of each other, and they're orbiting around the sun. And I'm going to explain how they make this cone shape by just looking at the dynamics of two orbits in the disk. So I'm going to select two orbits that are located 180 degrees opposite each other. I'm going to see what they do to each other. And then I'll show results from an actual n-body simulation. So this will explain the mechanism, first of all. So there's going to be a few things on this slide, starting at the top left-hand side. The amount an orbit rolls, I call this IA. That's not so important, but you'll see it on the next slide again. The reason for this is we call it inclination due to rotation over the semi-major axis. But again, not important. The amount an orbit pitches back or forward or back is called IB. And then there's the two equations I showed you before. So we're taking the one orbit in the disk. On the top right-hand side, you see a face-down projection of the disk. So we're taking the red orbit here. And what I'm going to do is going to perturb this orbit very slightly. And I'm going to do this with a perturbing force, which I've depicted here, at aphelion of the orbit. The orbit starts in the reference plane, in the orbital plane, and we're going to say, what does this force do to this orbit? Does it rotate it? Does it do nothing? And we can just use the equations here to figure it out. So the j vector, or angular momentum vector of this orbit, can be calculated at aphelion by looking at the radius vector times some velocity vector that it has at aphelion, and that will give you the j vector that points directly upwards here. Now, what is the force going to do? It's going to gravitationally torque the orbit, and you can calculate the direction of this torque by saying r cross f. So your radius vector crossed with your force vector is going to give you a torque that runs along that b axis there into the plane. So what that means, because torque is rate of change of angular momentum, is that the new angular momentum vector is going to be directed more towards b, so the orbit rolls to its left. In units of IA and IB, it means it has some negative IA. OK. Now, I'm going to ask, what does that do to an orbit directly across from it? Let's say we take away that perturbing force. And now we have a flattened disk, but just one orbit is rolled. OK, so the orbit, the blue orbit, that's located 180 degrees opposite it, it's now going to feel forces on the sides of its orbit that it didn't feel before, just because the orbit opposite it rolled. So the forces are directed up here, down here, and we can again just calculate the torque from r cross f. And you'll see, if you use the right-hand rule, that the torque is directed along the a direction here, which means the angular momentum vector is going to be rotated towards me, or in other words, that the orbit is going to pitch forward. So one orbit rolls, and the other one responds by pitching forward. And now that pitch forward lifts the aphelion position off the disk, and most of the mass of eccentric orbits is located at aphelion, which means you've created a net force above the plane, which is exactly what you needed to start this perturbation. So orbit 2 responds to orbit 1 by creating a force off the plane that makes orbit 1 roll even more. And that makes orbit 2 pitch even more. And so this is just a toy model with just 2 orbits. But you can see in this way that with just the slightest little perturbative force that you would expect in the solar system, just through noise or something passing by, the orbits are going to want to roll and pitch. And they will keep doing this to all the other orbits in the disk in a very particular way. OK, and this toy model, it's very simplistic, but it makes a lot of predictions. And then we can go to numerical experiments and check whether or not they bear out. So I'm just going to show one slide of results. And again, there's quite a lot going on in the plot, but there are 3 main things I want to point out. So the first is that I'm showing the top line, the yellow or mustard color, the median the median inclination for a bunch of orbits that I set up on high eccentricity orbits in a flat plane. Not perfectly flat, there was some numerical noise in there. And so I'm just looking to see what's the median or roughly their average inclination. And the shaded region indicates when sigma, or basically the majority of the orbits, are captured in this region. So what you see is that up until a certain point, the disk is quite flat, and then the inclinations all rise rapidly. And they all rise rapidly. It's not a diffusion process. It's not that some stay at low inclinations and others scatter outwards. This is a secular process, and they all go together. And it's actually an exponential process. And I've plotted the inclination in radians here. They reach something like 60 degrees on average. And some actually go retrograde, and some are a bit lower in inclination. OK, so it hasn't worked out perfectly. The red line is the average IA value, and IA is how much orbits roll. So what you see here is all the orbits, at the same time the inclinations start rising rapidly, they all get the same IA value, meaning they all roll. And in this scenario, they go positive. So they're all rolling to the right in this situation. All of them do it together. None of them roll to the left because of this mechanism I described. And in an analogous way, all the IB values are the same. So they all pitch. I think it's forward or backward. I'm not even sure in this scenario. And IA and IB are always in opposite signs, which is another prediction of the model. OK, so the last thing I want to show here is in terms of this omega variable, what this looks like. Well, we start off with all the omega variables randomized for the orbits in this disk. But once the inclinations start rising and they all start rolling and pitching in exactly the same way, they all squash down to very small distribution in omega values. And over the whole length of the simulation, the omega values change, but they all change together. And that's because the angular momentum vectors still precess, but they precess together in the simulation. OK, lastly, I want to point out the timescale. So this will happen no matter how much mass you put in the minor planets as compared to the sun. But the time scale for it to occur will change. And I've plotted time in units here. The mass of the sun divided by the mass of the planets times some orbital period, which corresponds to kind of the average orbital period of the minor planets. So if we give the minor planets about 1 Earth mass, and they orbit at 100 AU, which is about 1,000 years, this would give a time scale of about 300 million years for, on this plot, a time scale of 1. So if there's 1 Earth mass in minor planets, that means this will happen at roughly 600 million years in the solar system. So we really need that much mass in minor planets for this to happen in the solar system. If there was much less mass, this wouldn't occur in the age of the solar system. If there's 10 Earth masses in minor planets, this will happen even faster. But this is one of the things we need for this model to work. And it's just self-gravity of the minor planets themselves. Nothing else is needed out there. So how would this look in our schematic of the solar system? Well, I have, again, depicted the gas and ice giants with the Kuiper Belt and then the Oort cloud. And so these objects lie in between. I'm just going to depict 2 for clarity. So in this narrative, these objects are coming from the scattered disk. They're being scattered out by Neptune, and they retain the perihelion distance corresponding to the semi-major axis of Neptune. But their self-gravity over a long time scale, hundreds of millions of years perhaps, eventually start collecting them together into this cone shape. And one thing I haven't mentioned yet, but to conserve angular momentum, if you start off in a flat disk and you suddenly incline all your orbits, those orbits have to become less eccentric. So the orbits, when they're, the orbits, when they're inclined off the plane, become less eccentric to conserve angular momentum. And I've got the equation here for perihelion distance to remind you that if you retain roughly the same semi-major axis, but you become less eccentric, you increase your perihelion distance. And what this means is that these objects just naturally detach themselves from the inner solar system through this mechanism. They become more highly inclined, less eccentric, and they break away from Neptune. So this is why they would look offset from the scattered disk population. And so what the solar system would look like is quite strange. We would still have the orbits of the major planets, roughly coplanar. We have the Kuiper Belt objects. And then we would have a population of detached objects that have to be much more massive than the Kuiper Belt, but they would preferentially be on one side or the other. So it would look quite different. It's not a symmetric population. And then, of course, that would extend out into the Oort cloud. OK, so to summarize these ideas, you get detached objects with this self-gravity mechanism because their perihelion distances increase as their eccentricities decrease. You get very high inclinations with no low inclinations because it is an instability. You see in these simulations that all of the orbits gain rapidly inclination and leave none behind. So it's very different than a scattering process. And finally, they all cluster in omega because they all cause each other to tilt and roll just due to self-gravity by themselves. So it is quite a strong prediction of the model, and it's easily falsifiable, that we should have a new Kuiper Belt that's far more massive than the current day Kuiper Belt at larger distances and preferentially lifted off the plane of the major planets. And this should be discovered, if it's there, by upcoming and ongoing surveys such as Pan-STARRS and DECam and also LSST. But to conclude, no matter which is correct, to explain the orbits of these detached planets in the outer solar system, we need more mass in the outer solar system. So it can either come from having more minor planets, and their self-gravity will do this to themselves naturally, or it could be in the form of one single massive planet, Planet 9. And so it's a really exciting time, and we're going to discover one or the other. Okay, thank you.
Very interesting. I'll ask the first question. So the Planet 9 paper also claims that the yaw of orbits, as you call it, the longitude of perihelion are also clustered. So another difference in prediction would be which trend holds up as we discover more, right?
Yeah, absolutely. Yeah, so I didn't get into that too much because I don't see that in my own model, and they see that in 6 out of 13 objects. So I think we need better statistics before we say that's definitely in there. Yeah, but I think it's a strong way of determining which hypothesis is correct.
Thank you. That was fascinating. I am inferring from the current slide that even if the 9th, 10th, whatever planet is found, it fits into your model on some level, like as just another planet that happens to be on the large end. You said 1 to 10 Earth masses. Is there, and I'm sort of bearing the Nice model in mind, is there an upper limit to the amount of mass in this region of the solar system that would, like a ceiling above which your model fails, or what are the boundaries? In other words, how many planets how massive can the planets be before this process looks different?
So to make sure I understand your question exactly, so if there is a 9th planet that's extremely massive, I think that really would dominate the dynamics, and then this self-gravity effect wouldn't, it just wouldn't be dominant.
10 Earth masses is extremely massive by that definition.
Yeah. So I think if we have both, if there's both 10 Earth masses of minor planets and a single 10 Earth mass planet out there too, I mean, gravity is still happening, but I think the gravity of that single massive object is really going to dictate the dynamics out there. Yeah, I think it's still. I think that would still dictate the dynamics. Don't ask me any lower. I'm not sure where the boundary would be. But definitely, if there is an outer planet out there, I mean, this effect is still real. It will still happen. But I think the massive single or double planet would really dictate the dynamics.
Is there like an upper limit to the total mass?
The total mass that could be out there
That can work with
in minor planets. So I think most theories for the dynamical evolution of the solar system say in the initial debris disk you had like tens of Earth masses that could be scattered outwards. But in simulations so far that don't take into account self-gravity between those minor planets, because it's very difficult to do, all of these minor planets just keep getting scattered either out to the Oort cloud or scattered back in. So there's not a lot of mass left in these simulations at the region of space where we see the detached objects. This helps retain all the minor planets because they detach from the inner solar system with this mechanism. So they could be sitting out there on much less eccentric orbits, harder to discover. So yeah, that's a prediction here. But you don't see that usually in dynamics papers because the self-gravity isn't taken into account.
have you, or do you need to take into account the effects of, say, inner parts of the Oort cloud?
Oh, inner parts of the Oort cloud.
When you're dealing with the self-gravity of the detached objects?
So I've not even considered taking the gravity of the objects in the Oort cloud into account. They're much more distant, and I don't know if anybody has an idea of how much mass is estimated to be in the Oort cloud, but
It's a spherical distribution, so it wouldn't be very high.
yeah. So what I am going to be doing next is taking into account the gravity from the innermost planets. So the simulations I've done to date were not even very solar system specific. I was looking at this in context of the galactic center. So I wasn't taking into account secular perturbations from like Neptune and Jupiter and things like that. I know the mechanism still works for messing with it, but I really need to do more accurate solar system type of calculations. So that might change some things. I think what that's really going to do is push out the radius or the semi-major axis at which this becomes really important. Yeah.
I believe I've also read a proposed explanation of a recent encounter with an extrasolar system mass. Does that also work? And also a comment that sounds to me like sort of an ad hoc explanation, but maybe it's the truth.
So I've read a couple of papers that propose that a close encounter with a passing star could explain the clustering in omega, if that's what you're referring to. Yeah. I think the one I've read most in detail was suggesting that a passing star deposited its own minor planets into our solar system, with high inclination and could cluster in omega. I do find that a little contrived because you have to not perturb the inner solar system as you pass a star very close to the inner solar system. And furthermore, you'd have to do it within the last, say, tens of millions of years. Because if there's not a lot of mass in minor planets, they're all going to differentially precess with respect to one another. And so their omega values are just going to scatter out of that clustering if nothing's keeping them in that. So I really think the Planet 9, the forcing mechanism, or just self-gravity themselves, is a little more easy to accommodate.
With the inner planets, the inner disk, I think the major effect is going to be there may be another timescale. That was what I was going to ask. I think that's going to be the most interesting thing, the simulations you have planned now, because they may require a more massive disk, since you've just been comparing it to the age of the solar system, but there may be a differential precession due to the effective J2 flattened distribution of mass. With respect to the outer, the theories of the sun capturing another Oort cloud, the only viable ones really with any reasonable chance of happening are in the natal cloud, where the relative velocities are small enough to have that any non-trivial chance of happening. But passages of stars, GMCs, and in principle the galactic tide, but I think this is far enough in. Have you compared the numbers with the galactic tide? That the galactic tide probably won't be that important.
No, I mean, galactic tide and passing stars are typically important for distances like greater than 1,000 AU, say like 10 to the 4 AU, things like that. I haven't seen any papers that suggest that they would be important all the way down to scales of hundreds of AU. I think you have to invoke very close passages of stars.
How many confirmed objects are there in your pink category that's your geometric inspiration for this work?
So the original Trujillo and Shepard paper was only 12 objects. Last year there was another one discovered that made it 13. Sedna's in there, yes, and Biden, that's its nickname. I'm not sure what it's going to be actually called. And so in the Planet 9 paper, they also only look at these 13. Now, if you look at the Minor Planet Catalog, there are more objects that actually fit into the strict definition of being greater than 150 AU and having a perihelion distance greater than Neptune. And so I included all of them in my paper. And even looked, even pushed down further in semi-major axis space. And I'm really very much convinced that the clustering in omega is there. Whether or not the clustering in eccentricity vector space that makes the orbits co-locate, I'm not totally sure about that yet, because it's less than half of the objects that cluster in half of the parameter space. So it's, yeah. We're going to need to find more minor planets, I think.
So, could that planet 9 be close enough to the inner Oort cloud to trigger a certain family of comets that are caused by perturbations? Planet 9?
So there's a range in parameter space that planet 9 could exist in. So it could be quite highly eccentric, maybe 0.6, 0.7 in eccentricity. And I think the value they're quoting is about 1,000 AU for its semi-major axis. So that means it could get out to distances around 2,000 AU. And if it's 10 Earth masses, I mean, off the top of my head, I would think that it could have repercussions for disturbing comets in the Oort cloud. But having not worked on this personally, and yeah.
Could we plot up orbits of comets and try to find an indication of whether there is or is not planet?
Definitely, I think that should be done. Yeah, I'm going to keep working on my own hypothesis. But yeah, I think it's great, this idea of a planet 9, because especially if you have all that mass concentrated in one object, it's going to have dynamical repercussions for other bodies in the solar system, which should be detectable. So it's cool.
Between planet 9 and a host of smaller objects.
Yeah, there are definitely different predictions for them.
So I'm a little confused. In the plots I've seen in the news, there's all these detached objects that are all clustered and have similar orbits on one side, and then people are pointing to the other side for where Plan 9 is. But so is Plan 9 part of these detached objects or not? I mean, I was under the impression that maybe Plan 9 was scattering anything that was near it. And so that's why they were all clustered on the other side of the solar system from it.
Okay, so it's not my work, so if I say something crazy,
Okay.
I'm not a spokesperson. How I think it's working, it's a secular mechanism as well. So it's not a scattering process. It's not just scattering particles that seem to be in a similar orbit. It's secularly torquing these objects. And the dynamically stable objects in the simulations they've run are 180 degrees opposite it, which is why in the press release you'll see the orbits clustered, and then they've put Planet 9 on the other side. Orbits that are more located towards Planet 9 are not on dynamically stable orbits. So it's just on a timescale argument, you wouldn't expect to see those orbits.
So if there was no Planet 9, then just from your mechanism from scattering off the outer giants of the solar system, we would expect not to have an asymmetric population.
Yeah, so yes, that's correct. So in this mechanism, where it's self-gravity, there is no reason so far, I still have to put in secular perturbations from the inner giants and things like that, but there is no reason why they would be all co-located in physical space, why all their eccentricity vectors would cluster together. Yeah, so that's a very different prediction between the two models.
I have a very simple question. How would dark matter influence any of these observations or this theory? Is any possibility of that? I'm not sure.
I really don't think so, because the density of dark matter, unless dark matter is acting in very different ways, the density of dark matter in the solar system is so small that it really shouldn't be affecting any of the orbits of minor planets or planets whatsoever.
This is really more of a question for Madigan and Brown, but maybe you know the answer or somebody else in the room does. If you put a 10 Earth mass object at 1,000 AU, is it actually a planet?
Yeah.
It has to clear its orbit, so that's the question.
Everything's on the other side. Yeah, so for this talk, I had to look up the definition of minor planet and things like that. So to be a planet, you have to be in direct orbit around the sun. You can't be a moon, which I think Planet 9 is safe. Yeah, you have to be have enough gravity that you're kind of a spheroid or ellipsoid in shape. I think that's fine. And yeah, you have to clear out your orbit. And I think 10 Earth masses at 1,000 AU, anything that it comes into contact with, it will scatter out. So yeah, I think it's safe to call it a planet. The definition of planet is kind of funny, right? Because like Earth hasn't cleared out its orbit, right? There's a lot of asteroids and things that are co-orbiting with Earth. But yeah.
Okay. So further questions. For further questions, you can come up to the speaker after the talk, and the speaker gets presented with absolutely fabulous, unique SETI mug that only the chosen people who have given talks can have.
Wow,
Let's thank Anne-Marie once again.
Thank you.